calculated, you'll see what C is, and you can plot it. So let's see if I've got this up here. Yeah, I said equal to 1. Crazy windows are popping up. Okay. Okay, good. So I have x e to 2y minus sine squared plus y squared equals constant. I said equal to 1. And there's what the curve looks like, at least in sort of the section. Okay? Remember, this is x and this is y. It's multi-valued. At this value of x, whatever it is 1, 2. Two values. Okay? It's not surprising. You have a hideous function like that. Usually it is multi-valued. Okay? But again, if you're doing a real problem, you know whatever C happens to be, maybe it was 1, and you know where you're operating, so you know which point on this curve, that you have to pick up. Okay? But again, here's an example of, this happens quite often when you have these nonlinear equations, the solution is implicit. Okay? It's not a single value function over here. Okay? It's multi-valued.
And this would be just one graph for whatever arbitrary constant of C
Yeah. And again, if you had your initial conditions, you know what C is. Maybe C equals -1. Then you can, plot that one. Okay. We have one, I think, coming up where there's actually some initial condition. Let's put this to sleep. Probably the best thing to do. Okay. Yeah, the next one is the initial value problem. I'll show you a plot of that too. Hopefully this won't interfere. I don't want to turn off the example 3. Everybody see over here? See that in the glare. In this form. Here I got dy dx equals, upstairs I get xy squared minus cosine x times the sine of x divided by y parentheses 1 minus x squared. Okay, so dy dx is equal to, upstairs I got xy squared minus sine x cos x. Downstairs, y paren 1 minus x squared. And we're told that y of 0 is equal to 2. Okay? And when we solve now, we should get the constant and everything, get y as a function of x if we can. Okay. Now, the fact that the derivative blows up at plus or minus 1, we should expect kind of funky things to happen at plus or minus 1 in the solution, right? Kind of indication, but we haven't solved it yet. And notice also I don't have it in the standard form, right? I got to put something dx, something dy equals 0. So let's just do that. So I have xy squared minus cos x sine of x. That's the dx coefficient, right? Xy squared minus cosine x dx equals that dy plus x squared minus 1 dy equals 0. You very careful. Remember, all our formulas that we're using assumed it was big M dx plus big M dy equals 0. So you have to put it in that form. So we got dx coefficient, x y squared minus sin x cosine x equals x minus 1 divided by 0. Okay, so that's our m of xy, that's our n of xy. Okay? And again, let's see if it's exact. Okay, we know we have a test for exactness. The partial of m with respect to y is equal to what? I get 2xy, right? Because x times y squared derivative is 2xy with respect to y. And that's it. Right?
You forgot the
You
one.
forgot the y.
Oh, I forgot the y.
You flip your 1 minus x squared.
Oh, over here.
Yes.
Yeah, something was going wrong. Thank you. Yeah. Okay. And what's the partial of n with respect to x? I get derivative of x squared minus 1 is 2x times y. I'll pick it up over there. Yeah, okay. So it's exact everywhere in the xy plane. Great. So now we know there's a function u of xy such that that's nothing more than du. Well, what's du? It's partial u partial x dx. So the du dx has to be that guy, which is xy squared minus sine x cos x. Right? Xy squared x cos x. And partial u partial y is the dy coefficient, and that's going to be x squared minus 1 times y. So du dx is xy squared minus sine cosine, du dy is x squared minus 1 parentheses y. In this case, and it'll be a little different. This one looks easier to integrate, so I'm going to do that. Okay, let's integrate this guy with respect to y. Okay? When I integrate that guy with respect to y, I find that u is equal to x squared minus 1, right? The integral of y dy is y squared over 2, plus some arbitrary function of x, right? Everybody see that? With respect to y, and just check it. Take my expression and take the partial with respect to y, that goes away, and I get x squared minus 1 times y, which is what I started with. Okay, now we gotta do partial u partial y, and partial u partial x rather, and see what that gives us. The partial u with respect to x, therefore, is going to be, that'll be xy squared, right? Differentiate the x, you get a 2x, cancels the 2, get xy squared plus phi prime of x. But I know du dx, okay? It's xy squared minus sine x cos x. Okay? And indeed, the phi dx is only a function of x. Notice how all the stuff in y cancels out. And again, if at this stage you solve for d phi dx and you got a y dependence, you made a mistake. So the derivative of phi with respect to x is nothing more than minus sine of x cosine of x. And there's two ways you can integrate it. I'm going to look at my final result. I think I've got a sine squared in there and do it that way. So phi of x is equal to minus 1/2 sine squared x. Right? So I differentiate that. I get a minus sine or sine is cosine. That wasn't too bad. Okay? So now what's our u? U is equal to x squared minus 1, parentheses, y squared over 2, plus phi of x, minus 1/2 sine squared x. Right? And the solution, I just set that equal to a constant, right? So x squared minus 1, y squared over 2 minus phi of x. Right? So the solution to the differential equation, the general solution, is x squared minus 1, and let me multiply by 2 also, right? So equals constant, multiply by 2, okay? X squared minus 1 times y squared, right? Minus sine squared x equals an arbitrary constant. Okay, now at this point we can get the constant. I had an initial condition. It says that the curve should go from the point x equal to 0, y equals 2. Let's plug in those initial conditions. At x equal to 0, y is equal to plus 2. Okay, be careful over here. X equals 0, that's a negative y squared, which is negative 4, right? Sine squared 0 is 0, is equal to c. C has the value of negative 4. Okay? So the solution to the differential equation we can actually write it here, is u equals constant. We got c is that. So you have x squared minus 1 y squared minus sine squared x equals negative 4. Okay? Now in this case, you can actually solve for y in terms of x, right? Bring this stuff to the other side. You got sine squared minus 4 divided by x squared minus 1. And you have to take a square root, remember? So the question is plus or minus. You'll use the initial condition, and you'll see that you have to take the plus square root. If you solve this for y, you'll find out that y is equal to the square root of 4 minus sine squared x divided by 1 minus x squared. And indeed, you plug in x equal to 0, you can see y is equal to 2. So everybody understand basically what I did? I basically solved for y squared. You'd have a plus or minus, but the ambiguity is removed because you know when x equals 0, y equals 2. So you have to take the positive square root. Yeah.
So how do you choose whether you should take your 5x as sine or as cosine? You could do either, right?
Yeah. I'm just looking at my result that I have, okay? You can, perfectly good question over here. The question that was asked, I think it's worthwhile to repeat. You see over here we had Diff dx is minus sine cosine. One integral you can write as minus 1/2 sine squared. You can also write it as 1/2 cos squared. Yeah. And what would happen over here is that you'd have the identity, if you use the identity sine squared plus cos squared equals 1, you'll get the solution I have. Okay. Perfectly valid. Yeah. There's no difference. That's what you notice I paused and I looked at my notes because I just want to see what I had written. That's all. But perfectly, both are perfectly acceptable, and they give the exact same result. They have to, right? Because you have a uniqueness there. Okay. So I guess this will be the last problem, so we can just talk about this a little. So we started off with, again, this was initial value problem, okay? Okay, to see if it's exact, we had to put it in this form, mdx plus ndy equals 0. Yes, it was exact. Okay, in this case, I chose to integrate the second equation rather than the first. That gave me an arbitrary function of x. And then I do du dx, I find dphi dx, I integrate, and apply the initial condition. And in this case, actually can solve for y in terms of x. Now, what's interesting over here is that, as I mentioned at the beginning, the derivative becomes singular at plus or minus 1. It doesn't exist. So it's not surprising that the solution blows up at those points, right? So probably some asymptotes at plus or minus 1. What does it look like in between? You just have to graph it. And that's what I'm going to show you right now. Okay? I have a plot of this function. Actually, I have even a little bit more for you over here. Okay? I think I did a direction field also. What? Got all these great programs that we wrote, might as well use them. So there's the original equation, your goal. dy dx is xy squared minus sine cosine of 1 minus x squared y of 0 equals 2. What I did is I superimposed the direction field and also the curve that went through 0, 2 in red. Okay, to get an idea what it looks like. Okay? So there's the direction field. And you can see, yeah, the guy that goes through 0, 2 looks like that kind of U-shaped guy. Okay? And then I could even have a plot just of the function itself. No, I guess that's the only thing that you have. Okay. I thought I had, but it's, you know what it's going to look like, right? Basically. And again, those asymptotes are at plus or minus 1. You go down the x-axis, see? And the solution looks like it's also an even function. Let's see if that is that displayed over here. Yeah, this is sine squared as an even function. Okay? So there's a solution in red. Okay? So basically what we do today. Okay. And oh yeah, one thing which I want to point out, and as soon as I lift it, you'll see it. You'll notice basically that if you look at the axes, it's symmetric with respect to the y-axis. The y-axis goes right up here. Is 0, 2. Okay? So that means if the point xy is on the curve, then minus xy is on the curve. Which means that in the solution, if I replaced x by minus x, nothing should happen. Nothing should change. Indeed, if you look at it over here, where's our solution? Yeah. Replace x by minus x, the x squared doesn't change, and sine x, which is sine, but sine squared x doesn't. So that proves that also is symmetric, just like the graph shows you. Okay, I think I'll be it for today. We've got a couple more examples.